Hello everyone, welcome back to the latest session. Let's try to pick up the thread of where we left off earlier. In the last session, we were looking at understanding the activated sludge process or the biological process, right, by applying mass balance. In that context, we applied the mass balance around the entire system, which includes both the aeration tank and the secondary sedimentation tank or the secondary clarifier. But we applied the mass balance twice. Once on the X, which is the biomass or the microorganisms, and the second time on the substrate or R waste or the food for the microorganisms. And we looked at some variables, let's see, right? Let's look at them. So I guess this is Rx net, rate of microbial growth net, let's say. And we also looked at theta C, which is a very important parameter, cell residence time or solid retention time, let's say. How much time will the relevant microorganisms spend in your system? So we got this, and from that we get that Rx net equal to x by theta C, that is also fine. And by applying the mass balance on S, right, or the substrate, we got this equation. Yes, we also have this R net, these are all R net, I guess, right. Why is this negative? Obviously because wastewater is being degraded, that is why I guess it is negative, if I may say so, right. Let us move on, and applying that and playing around with the relevant variables, we come across this. And what do we see? We see that it is a function of theta C or the cell residence time or the solids retention time. It is not dependent on the flow of wastewater or such, but the concentration of substrate in the effluent is going to be dependent mainly on the cell retention time or the solids retention time, let us see. That is something to keep in mind, right. And then let us move on. What have we started looking at? We need to look at another application of mass balance, but we are going to combine the rate equation for biomass growth. What is the rate equation for biomass growth? Rx net is equal to rate of production of X minus rate of loss of X. Rx net, what was that? I think equal to x by theta C, if I am not wrong. Let me go back and check out here, right, that is x by theta C. Rate of production of X, you can write it in different terms, but now we are going to write it in a different way, minus rate of loss is Kd, decay constant, into X. We know that the microbes, how are they being formed? Let us see, how are they being produced? They are being produced when the substrate is being degraded, right. While the food is being degraded, part of it is being used for cell synthesis and the microbes are being produced. So we know that rate of production of the microbes will be dependent upon rate of loss of the substrate, let us say. And we already calculated this earlier, R net S. So we know that only a fraction of Rs will go towards cell synthesis. So I will have this yield coefficient, right. What is this giving me an idea about? How much cells or biomass will be produced for how much or a unit substrate or waste. That is what it will give me an idea about. So I can keep a negative here because Rs is negative out here, right. So let us play around with it or substitute that particular relevant aspect out here. But I think because we are taking Rs to be minus S naught by S, so let us not put that out here. So x by theta C will be equal to y into Rs net. I think we calculated that here. Where is that? Okay, equal to minus S naught, minus of S naught minus S by theta, minus of S naught minus S by theta, minus Kd into X, right. So here you can play around, right, and what do we get? We can solve for X, right, we can solve for X out here, we can solve for X, and we end up with this particular X, right. X is the concentration of microbes that need to be maintained in the aeration basin, let us say, right. And that is dependent upon various variables, not just theta C. It is also going to depend upon the water, how often or how much time is the water going to be present in the system, right. For example, if theta is high, as in if the water is going to be present in the system for longer time, then X, obviously you can see the effect, let us say. Unlike S, which was depend only on theta C, here we see that x is dependent upon both theta c and theta. That is something to keep in mind, let us say, right, and yield coefficient and decay coefficient and such, but let us move on from here. So, okay, I guess I already mentioned this: substrate, function of theta c, biomass, theta c and theta. So, one aspect to note is that, okay, so I guess I should look up the equation here as theta c, right. Okay. So, what do we see here? As theta c goes to its minimum, let us say, okay, and if the minimum is 1 by mu max minus k d, right, as theta c goes towards this minimum value, right, this minimum value, what is going to happen out here? What do we see? Then the denominator turns out to be 1 minus 1, 0. So, when theta c or the cell residence time decreases to its minimum, cell residence time or solids retention time, meaning how much time the microbes are going to spend in my system, as they decrease, what is going to happen to the substrate concentration or the wastewater BOD in the effluent? It is going to go to infinity, right. So, that is what it gives you an idea about. If the microbes are spending less time in the system, then there is not enough time for the microbes to degrade the relevant wastewater. So, that is why the substrate or the concentration of your particular compound of interest, which here is BOD, in your effluent is increasing. So, that is what we see out here, right. So, S goes to infinity as theta c goes to this value, which is the theta c minimum. And another aspect is, if we play around with the relevant values, we can come up with Rx net by Rs net, right. This Rx net will also take into account both the rate of production and rate of loss, right. Earlier we only looked at Rp and Rs and looked at Y, let us say, right. Here if we are looking at Rx net by Rs, we get the Y observed, and that is nothing but we can play around with the variables, pardon me, it will be Y by 1 plus Kd into theta c. Thus, you see that the decay coefficient or the decay term also comes into picture, right. Here is the observed one, right. Yield, I know that, from this waste, from this much waste, this much biomass will be produced, let us see. But I know that, this biomass is also going to die. So, if the look at the observed yield, so this is what it is going to look like, let us see, slightly lesser, if I may say so. That is something to keep in mind. So, one more mass balance relationship, I believe this is the last one. We are going to apply the material balance, right, and we are going to try to look at the relationship of the recycle ratio and the recycled solids concentration. Why is this important? We have our activated sludge process out here, fine, and that we know that there are two aspects, one is the aeration and one is this particular secondary settling tank or secondary clarifier where the sludge is settling down, and thus comes out like this. Why is this that we are recycling some of it? Because here we need to maintain microbes, right, and we know that the microbial concentration here is almost 0, the microbial concentration coming in. So, I need to know how much of this sludge do I need to recycle back into my aeration tank and how much I can waste here. So, this is critical out here, right. So, that will obviously depend upon how much or how well the sludge is settling. For example, if the sludge is settling very well, right, meaning the concentration of the microbes in that settled sludge is going to be very high, then my recycle rate need not be very high. I can make do with relatively less recycle flow. But if my sludge is not settling well, as in my plant is not being operated well. So, when I say sludge, I am referring to the suspended microbes and they are not settling very well, let us say, right. What is going to happen? Then I have to increase the recycle flow, and if I do not, then obviously the plant is going to be affected again. So, here we are going to look at steady state balance around the clarifier. Keep in mind that until now we looked at the mass balance around the system, entire system, but now to be able to understand the relevant recycle ratio, if I take this to be my entire, what do we say, control volume, right. If I take that to be my entire control volume, I will lose out on the recycle flow, right. Is the recycle flow coming into picture? No, because it is within the system, I will lose that information. So, now what is it that we are trying to do? We are trying to apply the mass balance around this particular system, around the clarifier, so that I will get an idea about the recycle flow too, right. So, let us look at what we have. I know it is Q out here, it is Q minus QW out here. Let me just erase this particular one so that it is relatively clearer. So, it is Q minus QW because QW is going out here, and this is QR, how much is being recycled. So, this flow coming into the clarifier will be Q plus QR, right. So, let us apply the mass balance. Again, we are not concerned about substrate, we are concerned about the sludge. So, we are applying the mass balance on X around the clarifier. So, let us see that again it is steady state. So, V dC by dt will be 0. So, if it is 0, how are the microorganisms coming into the system? Only by Q plus QR into X, let us see, right. And how are they leaving the system? Via 3 means, what is that? One is Q minus QW into X effluent. Here note that I am assuming that some microbes are leaving from this treated wastewater. This treated wastewater which is above, after the suspended solids are removed at the bottom, right, or the suspended microbes are removed at the bottom, the treated water is the supernatant and that is removed. But we are assuming that there are still some microbes in the particular system. Some people do not, then obviously X effluent will be 0. How else is the microorganism or the microorganisms leaving the system? QW, right. So, QW into XR. Why R? Obviously, this settled sludge, the concentration will be pretty high. And what else? We see that it is also being recycled, QR into XR, let us say, right, QR into XR, that is how it is also leaving this system, right. And are there any reactions occurring that affect the microbial concentration? We know that in the clarifier we are assuming that no concentrations, no reactions occur. So, we can go ahead with what we have and assume that the reaction term is 0. So, we have this out here. Let us see what else we need to do. So, obviously, it is simple to say we are trying to calculate how much we need to recycle, let us say QR, let us say, right. The term in brackets can be substituted with the definition of theta c, as in some of the terms in this brackets, or I guess after I play around with this rather, can be substituted with theta c. Let us see what we have. Theta c is this particular term out here. So, I guess I am not going to look at the algebra, we can play around with that, and once I substitute with that I will come up here. One aspect I need to mention is here X is the concentration of the microbes, VSS, let us say, right, MLVSS or VSS, volatile suspended solids. But typically you have your X dash, which is the total suspended solids, this is VSS. And for a particular wastewater, based on experience or such, you can know what is the ratio of this VSS by TSS, or what is the ratio of X by X dash, let us see, okay. So, 0.6 or something like that. So, based on that you can replace X with X dash, that is why we replace this. If not, the actual, what do we say, QR will be equal to how much recycle will depend upon Q into 1 minus theta by theta c into X recycle minus X, let us say, okay. So, this does not really look right, okay, I understand. So, it has to be X dash by this, right, or X dash by this, right. So, minor correction there, X by X recycle minus X. So, this is how you will calculate how much QR is required. So, what are some of the aspects that you need to be concerned out here. So, one is obviously XR. If you look at the equation and also understand the system, if the XR, let us say, is high, right, as you can see, if XR is high, then you can make do with a lesser QR, right. If XR is high, you can make do with a lesser QR. Why is that? XR meaning how much sludge or how much is the concentration of microbes in the settled sludge. If the sludge is settling well or it is good settling sludge, then the concentration of microbes that I am going to recycle within a unit or a particular flow rate is going to be pretty high, let us say, right. We are always concerned about the mass, right. But if the sludge is not settling well, obviously then I have to pump more of the relevant sludge, let us say. So, that is something to keep in mind. So, in that cases, obviously again we are going to have issues with steady state and such, but that is one aspect to keep in mind, right, that XR and QR, we have what do we say, close relationship out there, right. So, let us move on and look at what else we have. So, also sometimes or such we need to look at how much biomass is being produced, let us say, right. So, let us look at this. Define overall production rate in terms of volumetric rate. Overall production of microbes is, what is this, V times Rx, let us say, right. And here Rx net, right, Rx is rate of production of your biomass, right, R net. And I think we already solved that. For that, Rx equal to x by theta c, let us say, right. And we have to substitute for x. Let me see if I have the equation written down out here somewhere. Okay, x is this, y by 1 plus kd into theta c, or y observed. We know that is equal to y observed into S naught minus S into theta c by theta, and Rx I know is x by theta c, let us say, right, and this is x, let us say, right. So, what do we have out here? Let me try to substitute this x term out here, let us say, right, y observed into S naught minus S right. So, that is what I have, theta c by theta, pardon me. So, what do I have? I will what do we say, cancel out theta c. I will be ending up with v by theta into y observed into S naught minus S. Let me see if we can simplify this further. Theta is equal to v by q, right. So, v by theta will be equal to q into y observed into S naught minus S, right. So, that will give me an idea about the overall production rate in terms of volumetric rate, let us say, right. So, again if you look at this, this much substrate is being consumed and this is the yield, observed yield, right. So, this observed yield will tell me and give me an idea about how much substrate is being turned into biomass, let us say, and if I multiply that by Q, obviously that will give me the relevant rate. So, that is what we have out here. Let us move on. Okay, I guess we already did this and this is what we already ended up with, right. So, we just looked at the equation. I think we got S naught minus S. So, probably the student made an error. So, it should be Px is equal to y observed into Q into S naught minus S. Obviously, S minus S naught will be negative and P observed or the biomass production can't be negative. We are having production of biomass, right. So, these are the terms. So, what have we calculated over this course and the not course session and the previous one? We calculated equations for X, we calculated equations for S, we calculated equations for calculating QR or came up with the equation. We know the biomass production rate, we know mu max or we understood that, we know that our rate of production of what do we say microbes or growth will be mu into x, right, mu into x, and that is equal to mu max into S by Ks plus S into x, right. So, we looked at different variables. So, whenever we are trying to design it, what do I typically want? I want to, what do we say, achieve a particular S, as in initially I have 150 milligram per liter of BOD and I want to end up with 10 milligram per liter of BOD. How do I go about it, given that the expected yield, as in for this particular waste, this is the amount of biomass that will be produced. So, I get these aspects and we can solve them. So, let us go ahead and understand, I guess. Okay, I have one other aspect. So, it gives you the mass flow of the biomass or volatile suspended solids produced. we need this VSS by TSS for biological solids to obtain the TSS mass flow. Okay, again 0. grams of VSS per gram of TSS seems to be typical, let us say. So, here from the MIT Open Courseware we have a comparison between a fully mixed tank, right. Let me change the ink color. This is with recycle what we looked at, and this is another case without recycle, but we will never or usually will not have or look at this practically. So, theta or retention time V by Q obviously. Theta C, so obviously if I do not have the recycle, whatever is coming in is going out, the microbes are not spending any additional time because there is no recycle. So, then theta C will be equal to V by Q or theta, let us see. But if I have recycle, obviously the theta will increase, right. So, that is what you see in system without recycle. Theta C will be less, as in cells will or the biomass or the microorganisms will spend lesser time than in the case with where we have recycle, let us see. Some of the variables might be slightly off and such, but again this is from, you can play around and look at the equations that we develop, let us see, right. So, substrate equation again here and here we already looked at this as we looked at it in our case. So, here it is only hydraulic retention time, here it will be cell retention time. Typically hydraulic retention time in this case will be typically much lesser than theta C. So, here that is why for given similar characteristics, the substrate or the effluent substrate or the BOD in the effluent will be much less for the case without recycle compared to the case with the recycle, let us see. And then you have the substrate utilization rate, right. Substrate utilization rate, different terms, we will not go into this for now, let us say, right. So, let us move on. So, the last aspect I guess is oxygen transfer, but it is pretty important. Why is that? In a particular wastewater what do we say, treatment process, 50 to 60% of your costs, maintenance costs are from pumping air in, right. Obviously BOD, oxygen demand, you do not want that oxygen demand to be exerted in the river, you want that to be taken care of in your wastewater treatment plant. So, you need to provide the oxygen right here. So, you have some aspects to consider, but we will look at this in a new session, and as usual thanking you for your patience, I will end this session.